Hi. So welcome to our first screencast. You're going to be watching a lot of these this year. I hope it works for you. So I just want to talk to you about the three laws of nature that have the biggest importance in environmental science. There's three laws of nature that really come into play in this class, and the first one of those is called the first law of thermodynamics. You've probably heard of this one before. We'll take each of these in turn as we go through. But the first law of thermodynamics is an important one, as is the second law of thermodynamics. And the third one is another conservation law, which is known as conservation of matter. So these three laws are really hugely important in terms of understanding ecology, and that's one of the foundational ideas of environmental science. So let's start. Oops, I'm missing something here. Okay, this is the supposed to say the first law of thermodynamics. Is it? There it is. Okay. So the first law of thermodynamics basically says that you can never create or destroy energy. That you can transfer it from one object to another or convert it from one form to another, but the amount of energy that is present must always be accounted for. The universe started off 15 billion years ago, whatever, with a fixed amount of energy in it, and that amount of energy has never changed by even 1 joule. So it can take different forms, but it always comes from somewhere and goes to somewhere. It can be transferred between objects or transformed between forms, but the amount always is the same. Take a look at this example. Sorry, I'm talking too fast. Drank too much coffee. I think I'm going to have some more. All right, so here I have a battery. This battery contains chemical potential energy inside it. The energy is stored in the arrangement of the atoms and the chemicals here. Now, if I put this into a toy car, this toy car then can take the energy that's in here and convert it into motion. But the car can't go forever because there's a fixed amount of energy present in the battery. So the energy that the car gets comes from the battery. The battery had to get it from somewhere else. The thing that gave it to the battery had to get it from somewhere else. Energy always has to come from somewhere and go to somewhere. That's the first law of thermodynamics. Now, the reason it's important in ecology is that everything needs energy in order to operate. Anything that moves or functions does so by taking advantage of energy. And since you can't create or destroy it, it has to come from somewhere. And that's, something that's pretty limited. There's only certain things that can provide energy. We'll be studying that this year. There's some sources of energy are available, but not a whole lot of them. And so a lot of times what you think is one source of energy is really another one in disguise. But I don't want to give too much away right now. But the reason it's important in environmental science is because tracing the flow of energy turns out to be a really important thing we do in environmental science. I don't know why it went backwards. Okay, I screwed this one up. I wanted you to see that first and then the pictures. Okay, but it didn't work out that way. All right, so here's the deal. The second law of thermodynamics is kind of an interesting one. What it says is that anytime energy is transferred from one object to another or transformed from one form to another, some of it always ends up as heat energy. Now, heat energy is energy in the random molecular vibrations of an object, and there's no avoiding this. It's like you can think of it like the energy transformation and transfer tax. You can transfer energy and you can transform energy, but you got to turn some of it into heat when you do. And there's never been a single exception to this rule ever observed. So we often talk about this being lost as heat because when energy becomes heat, it's very difficult to make it turn into another form of energy. So there are ways, we'll study this year, that you can turn heat energy into electrical energy and kinetic energy, but it is not easy. It turns out usually once you turn energy into heat, you've kind of lost it because apart from being warm with it, you can't really do much with it. So what this is showing is like a pendulum. So if I put some energy into a pendulum and release it, it's going to go back and forth and back and forth. It will never have any more energy than what I put into it. So if I gave it 1 unit of energy, here it has 1 energy of what's called 1 unit of potential energy, then it has 1 unit of kinetic, and then 1 unit of potential, then 1 unit of kinetic, then 1 unit of potential. But that's not really true because in reality what happens is it starts off with 1 unit, and by the time it gets to here, it's already lost a little bit to heat. So instead of, let's just go with 100. Starts with 100 units. Now it's got 95, Now it's got 90. Now it's got 85. Now it's got 80, and so on. It always loses them until eventually it stops. The second law of thermodynamics explains why things end up stopping. They don't go forever. All right, you can't have a perpetual motion machine. The reason it's important is that in terms of human civilization, we rely a lot on energy, and a big part of our environmental degradation is a consequence of looking for sources of energy and expending them. But it turns out, because of the second law of thermodynamics, we end up wasting the majority of it. About 70% of the energy that we access, we just waste by turning into heat. So your generation, if you really want to be effective at conserving the energy that the world has and protect the environment, you should try to focus on finding a way of conserving that energy and keeping it from getting converted to heat. The other thing that's important about this is in ecology, we have what's called the 10% rule we'll study, which basically says that organisms give off heat, and that you right now are giving off heat. You're wasting some energy making heat, and that just is lost from the system. So there's a certain amount of energy that comes into a system in terms of food energy, but then that food energy, most of it gets wasted as heat energy. And that's going to be a pretty important concept in this first unit of study. And then I did it again. Don't you like these pictures I drew? I was really proud of these pictures. Okay. Those are supposed to be balloons, by the way. Okay. So this is a hydrogen balloon. This is an oxygen balloon. This is a beaker of water. I thought it was pretty clever. I even did the stoichiometry somewhat to get this numbers. Fudged a little bit. But conservation of matter is another really important law. But basically what this is just like you can't create or store energy, you can't just create or store matter. If you start off with 2 grams of hydrogen and 10 grams of oxygen, you will end up with 2 grams of hydrogen and 10 grams of oxygen. That can be rearranged to become 12 grams of H2O. But at the end of the day, the total amount of hydrogen you start with, the total amount of oxygen you start with is the total amount of hydrogen and oxygen you ended up with. You can't create or destroy matter. Now, it is possible to turn energy into matter, matter into energy, but we're not going to worry about that at this point here. Okay, so those are the 3 big ideas that are really the driving forces behind an awful lot of this course this year. So again, I guess I sort of jumped the gun here, but let's just say, why is the conservation of matter so important? Well, I would say one of the main reason it is because we can't make more atoms. So if there's an atom that's important to us, you either recycle it or you lose it. Okay, so for instance, in a natural system, in order to build proteins, in order to build cell walls, in order to build nucleic acids, you need nitrogen, you need phosphorus, you need some others, but nitrogen and phosphorus are biggies. You know what? It's easy to run out of nitrogen. It's easy to run out of phosphorus. So when you run out of these particular atoms, you can't build living systems. So the availability of certain atoms often limits how much life is possible. So what we see in ecology is there's this recycling that happens with certain types of atoms, like the ones I just mentioned. The other thing is, in human society, there's certain atoms we find very advantageous for technological purposes, like neodymium. We all like that because they use this for making the rare earth magnets that drive our headphones. Uranium is very valuable in terms of energy production. Tellurium, I forgot. Oh, I know. Tellurium is used in solar cells. Okay, and helium it's used in party balloons, but it's hard to get anymore because we're running out of helium, and so it's mostly used for medical experiments involving refrigeration. So they're becoming scarce, and as they do, they have to be either recycled or they can't be replaced. You can't make more of them. Now let's talk about closed systems and open systems. So a system is just a collection of objects that we define on our own. Okay, a terrarium is a great example of this. So if I have a terrarium, a sealed terrarium, one that's corked up, is essentially it's a closed system when it basically the matter that's in here can't get out. So a terrarium is closed with respect to matter. So if I start off with 500 grams of matter in here, 1,000 years from now, if I don't uncork it, I will still have 500 grams of matter. Matter is conserved. You can't get more of it. You can't make it go away. If you don't let any in or out, you'll always have 500 grams. Now that it could look like plants or more or less plants, but I have a total of 500 grams to work with. I can't end up with 7 kilograms of plants growing inside here. An open system is one that material can come in and out of. I'll just say stuff because it could be matter or energy. Stuff can go into or out of the system. So if stuff can go into or out of it, let's just talk about matter. So if I have a terrarium that is not a closed system, well, I could start off with 500 grams, and after a while, I could end up with 600 grams because I absorbed 100 grams from outside the system in terms of incoming water and carbon dioxide. Now, Earth is both a closed and open system. It is closed with respect to matter. Very, very little matter comes into Earth. Some comes down in the form of, space debris, meteorites, things like that, shooting stars. But and some things leave. Rocket ships do leave the planet. But overall, percentage-wise, it's closed system. No significant amount enters or leaves the planet Earth. So we're a closed system in that regard. But when it comes to energy, we're very much an open system. Light energy comes in from the sun. Infrared energy comes out from the Earth and goes back out into space. So energy flows in and out of our system all the time. In fact, it turns out that every system we know of in the universe is open with respect to energy. You can't close off energy the way you can close off a terrarium full of atoms. And that has to do with the fact there's a special relationship between thermal energy, that's the movement of atoms, and light energy. They're totally connected to each other. So let's just explore this briefly. Thermal energy is just the molecular vibrations of atoms. It's the kinetic energy, the energy of motions that atoms have because of their random vibrational motions that they have. So when something is cold, its atoms are moving slow. When something is hot, its atoms are moving very quickly in a random fashion. We call this thermal energy. Well, atoms, if you recall, are made out of charged particles. And when you move a charged particle, that's how you make light. So it's impossible to jiggle atoms without producing light in the process. Both kinetic energy, the kinetic motion is energy, and light is energy. So because energy is conserved, you can't create or destroy it. As an atom moves, it makes light energy, but as it makes light energy, it has less energy left in it, so it's going to slow down. So this is basically just showing you an electromagnetic spectrum. I have high frequency, high energy light up here. We call it gamma rays or X-rays. Ultraviolet, the light we can see visible from purple or violet is the higher energy end of it. Red is at the lower energy of it. Longer, lower energetic waves are called infrared, and then microwaves, and then radio waves. So let's just look at it this way. Red hot. We all have heard the term red hot. Red hot starts at about 500 degrees C. So if you're below 500 degrees, you're not visible to our eyes. That doesn't mean you're not giving off light. You're just giving off light our eyes don't see. You're giving off infrared light if you're close to 500. Well, you're not close to 500, really. What are you, like 36, 37? You're giving off infrared light. Things that are much colder give off microwaves, and things that are really, really cold, close to absolute zero, they give off radio waves. But all objects in the universe give off light because atoms, when they move, if an atom has temperature, and all atoms do, then they move. As they move, they give off energy. Slow ones give off radio waves. Once they're shaking at about 500 degrees, they make red light. And once they're shaking much faster, they give off purple light. Once they're going really fast, they give off ultraviolet light. And most things don't go fast enough to give off these, but it can be done in other ways. Not too important to our subject. So I just have a little graphic here to try to get this idea across. Okay, so I have an object that's not particularly warm, say room temperature. Okay, all objects are always giving off light because their atoms are shaking, and shaking atoms make light. Now what happens is if I expose this room temperature object to, say, sunlight, that light energy comes in and this object gets warmer. You've noticed this yourself. If you went camping, you're all cold and you get up in the morning and the sun comes up, you hold your hands up, you just feel that light energy hitting you and you warm up. As things get warmer, the atoms start moving faster. As the atoms start moving faster, they start giving off more energy, more light energy. And then as they give off more light energy, that causes them to cool back down. So there's always this interplay of atoms absorbing light, which makes them shake faster, but as they shake faster, they give off light and cool back down. And that's basically a really crucial idea in terms of Earth's energy budget. When we study global warming and things like that, we have to keep this in mind. So here's a graphic I have to show that here. So the sun sends solar energy here. Some of it bounces off. We don't absorb it. But when we do absorb it, the Earth gets warmer, and as it gets warmer, it gives off higher energy light. So the Earth is constantly giving off energy and constantly absorbing energy. And the idea is, if the world stays at a constant temperature, that means it gives off as much light as it takes in. It turns out, because of global warming, we're taking in more light than we give off, and as a consequence, the world is getting warmer. And I think that's all I've got for you here. So thanks for watching this. I'm going to post a homework assignment for you to do. So please make sure you check to see the link I have for that. Thanks.